So with limited resources, today, working out of my own garage, we are going to look at what makes an air conditioning compressor function. Back when I was a kid, a long time ago, some compressors were V-style compressor. They had a crankshaft and a couple of pistons. They looked a lot like a V-style engine. Nowadays, most of them are not of that design. Most of them use double-ended pistons, and they're driven by something called a swash plate. And in each end there are valves that control the inlet and outlet of the compressor. So what I'll do is I'll show you. We'll take apart a compressor. We'll see what the insides look like. We'll talk about the air conditioning clutch a little bit. I have a new clutch and clutch coil here, and I brought my power supply along so we can energize that and see how that works. And I have a mock-up cutaway that we can look at when we're all done and see the compressor actually functioning, see the pistons moving back and forth. So that's what we have for today. I don't know as far as the condenser on that GMC pickup. I still don't know if that will get done before the semester ends. I am going to order parts for it. Maybe I can do that here and just manage to do the evacuation and charging after the restrictions are lifted on the shop. Alright, here's a typical air conditioning compressor. This particular one, I don't know what it's out of. Again, these are things that were just laying around the classroom, but it's pretty typical 10-cylinder. I'll show you why I call it a 10-cylinder in a little bit. I have the clutch drive plate not fully installed on this because just to save time, in order to remove it actually requires a puller. So I just have it kind of set in place. Let me see if I can remove that just with my hands. Okay, so we'll go into the clutch assembly in more detail later. So you can see here where the belt drives the clutch, and the electromagnet engages it to our drive plate here, but like I say, that's for later. So see if I can get this off without too much trouble. There we go. So just the pulley for our belt has a bearing in here. And of course our clutch coil, big electromagnet. So we'll see if that will come off without too much difficulty. I'm working on kind of a wimpy tabletop here, so this could be a little bit challenging. Okay. It's just kind of pressed on there. Not the most elegant way of removing it, but so here's the compressor itself. Notice it's held together just by 4 long bolts that run from the front to the back. On the back of it here we have the suction and discharge ports. On the front, down inside, is a seal. Those seals sometimes go bad. Refrigerant oil can leak out of those. Those are replaceable. And then the drive shaft in the center here, which is splined, and the drive plate splines on there and spins it. So we'll start by removing these 4 bolts. Alrighty. 4 bolts loosened and removed. Now we need to separate the compressor at its half here. Really not too difficult to get it apart. A little pressure between the halves here, and we can remove the top section. So the top housing here, you see has some passages for refrigerant to flow. We have the valve plate. So we'll have to get into a little bit more detail about these valves, inlet and outlet valves. They're reed valves, so let me set that aside. And look at the actual compressor pistons. So 1, 2, 3, 4, 5 we have here, so you might think this is a 5-cylinder. And if I can hold this steady while I try to turn it, let me grab something to turn that with. You can see, no way it's going to happen that way. So we said there's 5 pistons, but what you have to realize is these are double-ended pistons. So on the back side, looks very similar to the front. We have another valve plate. If I remove that, keep it together. You can see the other end of the 5 pistons. So when this compressor rotates, the pistons move, you know, as this one is moving down, the one on the opposite end is moving up. So each piston actually is operating in 2 different cylinders. So let's split the halves here. This gets to be a little bit of a mess. So you can see the 5 cylinders on this end. 5 double-sided pistons. Now when I pull these out, easier said than done. Okay. Just trying to go far enough to remove them without getting crazy. Alright, well, we got crazy. So, you can see what each of these pistons looks like. So, the center is where the drive plate pushes back and forth on it. Piston head, it has sort of a piston ring on it. And here is the swash plate. So essentially, as the swash plate turns, it brings the piston to the right, to the left, to the right, to the left. So just by rotating, the rotating action is turned into the reciprocating motion by the swash plate, just pushing the pistons back and forth. You know, here's the housing in the back. You've got your inlet and outlet ports. So we have inlet and outlet valves in our valve plate that allow the refrigerant to move in only one direction in and then one direction out. So let's look at how that functions a little bit. So the reed valves are really very simple. It's just a plate of flexible steel, and when pressure is put against it, it can bend. So you can bend outward, and then it's spring-loaded back. So, you know, refrigerant will be allowed to move out from this chamber, but then if it tries to move back in, the plate's just going to seal against it. On the other side here, you pull this little spring off, same idea, reed valves. So refrigerant can push the valve out, but if the valve tries to go backwards the other way, it slams shut. Really, really simple device. Let's take a closer look at this valve plate There's two of them in this compressor, of course. You know, one in the front and one around on the back side. You saw that, right? So, take these different pieces apart here. We got the valve plate itself. This is a relatively heavy steel plate. Various passages drilled in it, right? Here we have the inlet reed. So this is a flexible piece of metal. Bends pretty easily. And, you know, this of course is in the passages on the suction side of the compressor. So for refrigerant to enter into a cylinder, it's just going to push and bend that reed valve open. So that's just gonna, let's get this in the right camera angle here. It's just gonna push it open. Okay, so that's the inlet reed. Here on the opposite side, and with the passages around the outside, we have the outlet reed. We're gonna use these dowel pins to align them, right? So the outlet reed, when the piston moves outward in the cylinder, that pressure is going to force that reed valve to bend, right? Refrigerant's going to flow out. This plate here is going to act, it's just got little, trying to get this where it's a good camera angle, but little stops to keep those outlet reeds from bending too far and snapping right off. So hard to see, I know. So we'll put this whole thing together. And I'm just going to set this aside a minute. Looking at the housing, you know, here's the front housing, right? In the center of that front housing is where all the refrigerant coming from the back is available to all those inlet reed valves, right? Those inlet reeds are in the center. Take these apart again. So they're going to be sitting in here like so. In the middle of the compressor, right? And so all of the pressure or all the refrigerant entering the compressor is in this center chamber. If we go to the back, right, we go to the back, we can see that actually the inlet port here, right? So the inlet port has an opening into this center chamber. All right, so the center chamber here, this is kind of like the intake manifold, if you will, right? And there's a passage right up through the middle of this compressor. Take this apart a minute. Right up through the center of the compressor that allows the rear intake manifold and the front intake manifold to connect together, right? So, and then around the outside, I guess you would say, is the exhaust manifold or the outlet manifold, right? This is where all of the pressure coming out of the cylinders eventually winds up. So coming out of these rear cylinders, it winds up around in this cavity here, and then it can move to the front through another passage in the housing and back down through eventually to the outlet port. So here's the outlet port, right, or the discharge port. So suction, discharge, you know, the suction port comes into the center. The discharge port is around the outer side. Again, your inlet reed valves are in the middle. You know, you can see they're in the center of the compressor, and your outlet reed valves are all around the outside. Alright, so where I have my valve plate, this is the one from the rear of the compressor, and let's put the pieces together. We have our inlet reeds. Okay, so as I said, you know, those are easily pushed in this direction, but they cannot open in the opposite direction. They're closed. I have my outlet reeds. Everything lines up with these dowel pins here. And then our springs. So that's the assembled valve plate. And so let's try to kind of look at the way this thing works. Let me set it on the end of the housing. And if you look down inside, it's a little difficult to see maybe in the light, but you can see there's an inlet valve and an outlet valve in each cylinder. In fact, let me get a little bit better light on that. Okay. See if there's a little bit better light, if you can see that more clearly. Towards the center is an inlet valve. It's a little bit bigger, and towards the outside is an outlet valve. So if we look at the way these passages are in the compressor, let me get this all back together. Here's our rear housing, and you know, here is our inlet port right here. So refrigerant is allowed in there. It gets to the center where it has access to all these inlet valves. Right? And then there's a passage in the housing that goes from the inlet here all the way through. So here's, you know, two halves of the housing, they mate together like that, and refrigerant can flow through that to the front of the compressor, and at the front of the compressor then it's going to have access to all the front inlet valves. As far as the outlets, same thing, the front and rear are connected together. There's a passage all the way around on the front, and on the rear, most of the way around, except for right at the outlet itself. That comes, again, from the front through a somewhat smaller passage in the housing. It's a little harder to see, but that allows it to go from the front to the back, and then ultimately, you know, out the compressor outlet here. So let's see if we can reassemble this. This is usually a little bit tricky getting the pistons in and the swash plate all at the same time, but we're going to take a shot at it. So we'll start with one, and just put another one in and roll it around, and see if we can get another. I don't want to get too far. Roll that around. There's one more. And if we are extremely lucky, we'll manage to slide this fifth one in without too much trouble. Not saying we're going to be extremely lucky. Okay. Next trick is getting them all lined up into the 5 slots. So we'll work on that. It's just a matter of very slowly working it in. Of course, if we were assembling this to actually be used in a vehicle, cleanliness would be very important, as would lubrication with the proper refrigerant oil. Okay. Things are looking pretty good. Just the the one piston seems to be giving a little bit of trouble here. Guess we are starting over. First I want to make sure that all of these go in no problem. That's that one. Both ends. This compressor's been apart. There we go. There's our issue. We've got a folded up ring. Okay. Looks like this has been abused once or twice. Trouble with working on things out of the classroom. If things are forced together. Alright. I'm going to pause and see if there's anything I can do about this. Alright, with a little additional finesse, we've managed to install all the pistons. You know, this one obviously won't go down any further until the one that's all the way down in its travel moves. So, you know, paying attention to line up our passages here with this one here. Now we'll attempt to slide the front housing on very carefully so that we don't cut these piston rings either. So you don't want to use any kind of force on this. This is just purely trying to get everything together. So, you know, the compressor is essentially together now, rotating. Sorry, you can't see that. As I turn it, pistons are moving up and down in the cylinders. Same thing happening on this side. It's spinning by hand, so I know nothing's too jammed up. Now we'll install the valve plates. So we have a couple little index holes here. There's a pin. There are 2 pins on the plate. We're going to make sure line up with those holes. And then we can set our rear housing on, paying attention to the plate alignment. And we have a half-assembled compressor that is still capable of turning. Alright, the next challenge, of course, we've got our front valve plate. So, same 2 dowel pins, same 2 alignment holes, right? So, you know, we can put these pieces on individually if we want, right? Just so you can see them better. Inlet valves sticking out into each cylinder, right? The outlet valves, so I'm gonna have to get these started together. I said outlet valves, I should have said the valve plate itself. Turn this so gravity, I'm not fighting gravity. Okay. So the inlet valves, the valve plate, now the outlet valves, and the springs. As long as we have everything lined up on the dowels, we shouldn't have any problem. So again, as these pistons move up and down, you know, refrigerant will go in through the inlets and then come out as the outlets deflect because of the pressure in the cylinder as the piston comes up. All right, now paying attention to my alignment again, put the front housing on. So I have the two dowel holes here. And of course, when we put this together, the bolt holes are going to line up, you know, with the front housing and the back housing. So it's pretty easy to see when things are close and you can just kind of feel when those pins drop into place, which happens very easily when nobody is watching. Looks like everything is lined up a little better now. I had to take that apart and adjust things a little bit. And we'll see if she goes together now. Oh, that's a lot better. Okay. And of course our bolts. Like I said, you know, even this center O-ring that seals the entire unit together would have gotten a coating of refrigerant oil. Of course, they would all be new as well. So make sure these are all started. Everything is lined up. I'll snug them down, and they should be torqued to spec. Okay, all the bolts torqued to spec. We drew them down evenly, so once you get this cocked, then you might have a problem getting it to slide together. You might cut the O-ring. So I threaded the screw back into the drive shaft, you know, the crankshaft for a better word, and we'll see it spins nice and easily, nothing's binding, no problem. So I'm not going to put the clutch back on for now because I want to do something separate with that, show you something separate with the clutch. Here I have another example of a compressor, similar, but there are some major differences between this one and the one we just looked at. So the one we just looked at had 5 double-ended pistons, making it a 10-cylinder compressor. This one, see, this is a cutaway, so I'm not going to take it apart, but this one instead has only 6, and these pistons are not double-ended. In other words, the cylinders are here, and the space above the cylinders is just the swash plate itself. So as I turn that, you can see how that swash plate moves and causes the pistons to go up and down, but it's only one-sided. You might notice, I don't know if you can tell, these pistons are bigger than the ones in the other compressor, so each one, you know, delivers more refrigerant with each stroke. The downside of that, of course, you know, the advantage of having the smaller pistons is that each pulse is smaller, so it's going to operate more quietly. If you have larger pistons putting out bigger pulses every time they, you know, push refrigerant out, you may be able to hear that kind of as a kind of a vibration in the refrigerant lines. A lot of times you'll see mufflers on the outlet side of a compressor to try to reduce that noise. Again, really difficult to see. This just has one reed valve plate here. You know, there's inlet reeds and outlet reeds. So this would be the inlet. It's going to be able to move in towards the piston, and the outlet is down here, and it can move away. I can push that outward. So, you know, another thing, the drive plate. So we don't have the clutch coil or the pulley on here, just the plate itself. That's what's allowing me to turn it. This one, the suction and discharge ports are actually labeled. Suction over here, discharge over here. So I want to point out this valve on the back, this spool valve here. This compressor, you know, the disadvantage is the bigger pistons and that they're not double-sided, so it might be a little bit less efficient. However, this is a variable displacement compressor, which means that the angle of this swash plate can change based on the output of this compressor. So when the compressor is spinning slowly, that swash plate is going to be at an extreme angle, and we're going to get a full strokes on those pistons. But as the engine runs faster, and this compressor is putting out more than it needs to, in order to reduce the load on the engine and improve fuel economy, some of that pressure is going to feed back and flatten this swash plate out somewhat, so that the stroke becomes smaller and the displacement in the output of the compressor actually becomes smaller, and that actually puts less of a load on the engine when it's not needed. Now it's time to talk about the compressor clutch. So, as I'm sure you probably realized, there are different controls on an air conditioning system, such as a thermostatic expansion valve that can control the pressure, the pressures in the system, and thereby controlling the temperatures. Another method of controlling those pressures is to cycle the compressor clutch on and off. When the low side pressure gets too low, the clutch is cycled off, and then when that suction side pressure gets high enough again, the clutch is cycled back on. So that's a cycling clutch system. So there are both systems. There are other reasons for the clutch to cycle off though. One of the most obvious would be if the driver turns the air conditioning system off. So the compressor clutch is under the control of the HVAC, the HVAC module, but also there may be some control from the powertrain control module. Some reasons why the powertrain control module might turn the compressor clutch off. Something called wide open throttle AC cutout. So when the driver goes to wide open throttle, obviously you're looking for maximum power. Maybe you're passing somebody, towing a camper up a hill. Either way, the AC compressor does take some horsepower. So when maximum power is wanted, the powertrain control module may turn off the AC compressor clutch. Another situation where it might do that, there is a high pressure switch that limits how high the pressure in the system can get. So if something goes wrong, if there were a blockage or restriction in one of the high side lines, or if the thermostatic expansion valve froze, the pressure on the high side might climb to dangerous levels. So that high pressure switch is going to feed a module, and that module, when the pressure reaches dangerous proportions, such as, see, and I think you can look this up. We'll look it up later. If memory serves me, it's somewhere around 450 psi that the compressor clutch will be turned off to avoid blowing out a line. If that doesn't work, then there is a mechanical relief valve, I think blows off at about 600 psi. So, in the event of, let's say, something else is causing the pressure to go high, not the compressor, let's say the car's on fire. So, that heat drives the pressure in the system up. Rather than have hoses blow, it's the relief valve is a more controlled leak to let pressure out. That's really a last resort for, saving the ozone layer. We don't want to let refrigerant out into the atmosphere, but if turning the compressor off doesn't work, we're not going to let the pressure rise indefinitely. At some point it has to be dealt with. So as far as the clutch, it may be turned off for other reasons than the HVAC module turning it off or the driver turning it off. So let's look at the pieces of the clutch here. This drive plate, it may look like one solid piece, but actually the center portion of it here is splined, or sometimes they use a Woodruff key and a keyway. That's splined to the input shaft of the compressor. So, and there's a bolt or a screw fastening it on. So whenever this plate is rotating, the compressor input shaft is going to be rotating. The outside of it, though, the outside diameter is a separate piece, and it's connected to the inside by these three springs. So what that means is that the center hub remains stationary. The drive plate here can actually move in this direction. So it can be pulled in towards the compressor. The pulley, so the pulley has a bearing in the middle, right? And it has the mating surface for that drive plate. This pulley is driven by the belt. So in this case it's a serpentine belt, older ones was a V-belt, you know, driven off the engine crankshaft. So whenever the engine's running, this pulley will be turning regardless of whether the air conditioning system is on or not. So if the air conditioning system is not on, you know, the pulley is free to turn while the compressor drive plate is stationary. So there will be a little bit of a gap between the pulley and the drive plate, so they're not dragging on each other. If there's too much of a gap, they may not engage together when they need to. It may slip. If there's not enough of a gap, it may not release when it's supposed to, and so it'll drag and it'll quickly wear out the plate. They're not supposed to be sliding against each other for a long period of time. When this engages, it's very quick, a very sudden engagement. There's not a whole lot of slippage going on here. So the spacing between these two surfaces is accomplished usually by a shim down in the hub here that, you know, you put a thicker or more shims in and it can push the drive plate farther out away from the pulley. It's checked with a feeler gauge in the spec. It's a pretty wide range, and I don't, again, we'll look this up afterwards. We'll fire up all data and we'll look at something typical. I think something like between 10 and 40 thousandths. It's really a big wide range, you know, but it has to completely release so they're not dragging on each other, and it can't be so far apart that it doesn't clamp solidly, you know, when it's engaged. So what engages it, I guess, is the next question. And that's where this clutch coil comes in. So the clutch coil is just a big electromagnet. To demonstrate that, I have my power supply that you've all become accustomed to. I need to plug it in here a minute. See if I can wake my laptop back up again, just so I make sure I can see what I'm doing. Okay, so here I have the power supply, right? You guys are all familiar with this thing. And I'm gonna hook, I'm gonna turn it off. I'm just gonna hook it to the terminals of this clutch coil. Try to keep them from coming in contact with each other, hopefully. And that's going to be challenging. See if I can turn this around, make it a little better. Alright, well, they're not actually touching. That's good. So, you know, right now it's not energized, so, you know, nothing sticks to it. Screwdriver here doesn't stick. Now you turn it on, and that screwdriver sticks pretty tightly to it. Turn it back off a minute. So the way this thing works, right, is behind the pulley. So let me set the pulley over it. And then the drive plate is here. When that electromagnet magnetizes, it can pull the drive plate against the pulley. So right now, I slide this piece of paper in here, I can pull it out no problem. Right? Now let me energize that clutch coil, and there is no way that that piece of paper is coming out of there. I really doubt that I could separate these pieces no matter how hard I try. So we turn it off and let the power go away for a second. and it's loose again. So I can slide that around now if I turn it on. There is no no way I can slide that. An idea, you know, that's going to pick the entire pretty strong. Now I turn it off, it drops. So to activate the AC compressor, get the AC compressor spinning, PCM or HVAC module, and you know, a lot of this depends on the vehicle and the age of the vehicle. The newer vehicle, the more likely the PCM is to be involved. So a module is just simply going to provide battery voltage to the 2 pins on the compressor clutch, the clutch coil here. That coil is behind the pulley, so you know the pulley is already spinning from the engine. So you know, here we have the pulley spinning, but the drive plate is not. And as you saw, when that so you know the drive plate is loose, when that compressor clutch kicks on, these are locked together, and there's no way that compressor is going to turn, or this clutch has to slip, and that's not going to happen easily. And then when the power is taken away, again, these little springs allow the drive plate, you know, it pulls it back away from the pulley, and again, the pulley can spin without the compressor clutch spinning. So just a little review what we looked at today, and then I want to look at a couple of things on ALLDATA just to kind of verify, you know, some of the things we've talked about. So today I took apart a 10-cylinder compressor. It was 10 cylinders because it had 5 double-sided pistons. So 5 cylinders in the back, 5 cylinders in the front. And we kind of looked at how the reed valves work. And then I talked about the AC compressor clutch. So some more practical things. I did look up, I talked about a high pressure cutout switch. I thought they cut out about 450 PSI. I was able to find one spec where it was 420 PSI. So in the ballpark, something like that. You know, it will, the point is, it will try to cut the compressor off before the pressure gets high enough to burst a hose or a component. If that fails for whatever reason, even if, you know, if the compressor keeps running, or if turning the compressor off doesn't stop the pressure from rising, then there is a mechanical relief valve, and I do believe that that's about 600 PSI, like I said. So let me just bring ALLDATA up here, and you know, there's a couple things. So if we replace a compressor, now why would we replace a compressor? You know, a couple of things can happen. If any contamination gets into the system, it can take out the compressor, score up the cylinders and things like that. If the system, probably the biggest problem is if the system somehow runs out of oil, you know, then we'd have to replace the compressor. So now I'll see if I can find it. If we have to replace the compressor, see if I can find this. What they're asking you to do is drain and measure as much of the refrigerant oil as possible from the removed compressor, right? We're going to measure it. The replacement compressor comes full of oil, so you don't necessarily want to put all of that oil into the system, because what happens is when the system is built, you know, there's oil in the compressor that gets distributed. Some of it lays in some of the lines, some of it lays in the bottom of the evaporator, some lays in the condenser. So, you know, when you take a compressor out, you're not getting all of the oil from the system out of that compressor. So you may have to partially drain it. So typically what you do is you measure what's come out of the old compressor. Then in another clean container, you dump everything out of the new compressor and put back into it how much you need. So let me see, I found it a minute ago, capacity specifications for refrigerant oil. Here we go. So if you look at this, it's kind of interesting, right? If there's abrupt refrigerant loss, so a line blows, you're going to lose probably most or all of the oil from the system. So it's saying you're going to add 2 ounces. 2 ounces is on this vehicle, I believe, how much a new compressor, 2 ounces of PAG oil, is shipped with, right? If you are replacing the condenser, they recommend you add 1 ounce. If you're replacing the evaporator, 3 ounces. Any line, hose or tube assembly, 1 ounce. But here there's a note: abrupt refrigerant loss due to large leak, hose rupture, collision, or the pressure relief valve opening. Anything that is abrupt refrigerant loss, then they want you, when you're replacing a line, put 1 ounce in. Conditions that allow the refrigerant to seep or bleed off over time do not cause this oil loss. So, upon replacement of a component that caused a large refrigerant loss, also add the required amount of oil for the particular component. So the way I read that is abrupt refrigerant loss, you're doing 2 ounces, right, here, and then let's say it was a line or a hose, you're doing another there. The total capacity is 5 ounces. So if I was to replace a compressor, right, then it says it comes with 2 ounces. The description, the procedure said it comes with the entire charge, which would be 5 ounces. So it's questionable. I guess what you need to do is drain out everything that came in the new compressor, so you know how much is in it, and then you're adding 2 ounces back into it. Okay. If the compressor does fail, and I've seen this, if you have a fixed orifice tube, it can plug that orifice tube. If you have a thermostatic expansion valve system, it can plug that thermostatic expansion valve. So the trouble with a failed compressor is it's going to leave residue throughout the system. So the system's going to need to be flushed, and you're probably going to need to replace the expansion valve. Also, if you're opening the system for any length of time, you really should be replacing the receiver dryer. So frequently they sell kits. Let me see if I can find this. If I go to Rock Auto, just for example, because I know I did this before, right? On I believe it was a 2003 Volkswagen. And this isn't the only car this would be true for. It's just that one I have experience with, I know I did this. 2003 Jetta, 1.8 turbocharged, and it was a AC compressor and component kit. And what it came with was the compressor itself, right? Compressor, a thermostatic expansion valve, and a receiver dryer. So the entire thing, the receiver dryer, has a filter also in it. So if that compressor grenades, it's probably going to plug up the thermostatic expansion valve, and that filter in the receiver dryer is going to be all full of pieces of compressor. So I would suggest that you at least replace these parts. Now, if you look at this little question, it says, should I also replace my condenser? And it says here, vehicle manufacturers recommend that the condenser be replaced whenever the compressor is replaced. Older tube and fin style can technically be flushed Metal shards can get lodged in the cylindrical tubes and restrict refrigerant flow, diminishing the heat transfer capabilities. So I don't know. I can tell you my experience with that Volkswagen was I replaced these three parts, the receiver dryer, uh, thermostatic expansion valve, compressor, and the vehicle went years after that without any trouble. Uh, so to summarize, the AC compressor is relatively simple inside. I'm sure you saw. The valves, the valve plates are really simplistic. Those reed valves. So how much can really go wrong? Probably not a whole lot. Sometimes those reeds they wear out. They're flexing a million times, and just like taking a beer can or a pop can, and you keep flexing it, eventually it's going to break. So you can lose those, and that would take out a cylinder. So the capacity or the output of the compressor would be diminished by that one cylinder. So in that 10 cylinder, we would lose 10% of the capacity of that compressor. Um, what else can go wrong? Like I said, if it runs out of oil, everything inside of it can just grind itself to death, and then you have big problems. You have junk scattered throughout your AC system. There's one other thing I was going to say. Oh yeah, so you saw me take apart a compressor. Chances are you're never going to do that in the field. Um, cost of labor versus the cost of remanufactured parts. Having to warranty things, think about it. If you take that compressor apart and fix it, now you're the guy having to do the warranty on it, right? If you replace it with a remanufactured or a new one, then that manufacturer or remanufacturer is responsible for the quality of that compressor. It's just important that you pay attention to the right procedure for replacing the oil that you lose, and understanding that if the compressor goes, you can't just slap a new compressor in. There's going to be, if the compressor came apart, if there's aluminum or steel grindings in the system, you can't leave those in there. They'll plug things up. The system will not function, and that grit may come back around and ruin the new compressor. So you need to think about what happened, and then from there, decide: do I need just a compressor? Do I need expansion valve? Do I need the receiver dryer? And the answer is almost certainly yes. Right. So what are some of the things you can do with a compressor that you're likely to do in the field? You're not likely to take one apart and rebuild it. The single biggest thing is probably replacing the compressor clutch. So there's something, let me go back to ALLDATA here, and I'm sharing. Let me make sure I'm still sharing here. So if I go back to ALLDATA, see if I can get back to that without. Yeah. So on this one, it's interesting. Parts and labor. I think I go to compressor here. Compressor HVAC. Procedures, okay. So there's just that. You get compressor shaft seal. This is really interesting. Gives us parts and labor. Here, check this out. So to replace the shaft seal, warranty pays 0, and customer pay is 1.3. That's pretty interesting. What that tells me is under warranty, it's probably a non-existent labor operation. In other words, they probably have you just replacing the compressor rather than replacing that shaft seal. If you're looking for leaks, that shaft seal, what can happen is if a system sits for a while without running, the shaft seal can kind of dry out and it'll leak. So you'll find traces of refrigerant at the bottom of the compressor behind the pulley. When the system runs and oil gets on that seal, sometimes it'll stop the leak for a little while. So if you're using, say, an electronic leak detector and the leak is from that shaft seal, it may not indicate a leak until the vehicle's been sitting for a little while and the oil drains away from that shaft seal. What else can I tell you about compressors? You saw the variable displacement one. Hopefully you understand the idea behind that is, why put engine horsepower into pumping refrigerant that you don't need to pump. So the displacement of the compressor can actually be reduced, thereby reducing the amount of horsepower it takes away. So going slow, you might need the full capacity of the compressor, but when the engine's spinning fast and the compressor's spinning fast, you can probably back down on the displacement of it and still have plenty of refrigerant flow to do the job. All right, so I think that about sums it up. Do the report. I didn't give you a whole lot of numbers here, so I just want to make sure you understand what a reed valve is, how that works. They can go bad, but I'm more interested in, the things that you can do something about, right? Compressor clutch. Here, let me look. I did not. Compressor clutch. Let's see if there's specs on that, because I talked about that. Okay, yeah. Clutch air gap. Remember I talked about that when I showed you the clutch. That's between that drive plate and the pulley. I said it was a pretty wide range, so 12 to 24 thousandths of an inch in this case. I've seen them up to 40, but that's for this 2010 Impala. So that's enough space that they're not dragging. So in other words, when it's released, it's fully released, but it's close enough that when that coil comes on, it locks that drive plate in solid. All right. So I almost forgot about that. I wanted to check that. Let me stop sharing this a minute here. So for the report, mention that spec, in fact. So I know you saw that, and mention why do we need to adjust the air gap. See if you remember how you adjust the air gap. That was in the video. That's, like I say, compressor clutch replacement. If you're going to work on a compressor, that is the single most likely thing you're going to do to it. The other most likely thing you're going to do to it is just completely replace it. So odds of repairing a AC compressor in the field in this day and age are pretty slim. So I'm looking forward to the reports. Hopefully you learned something from this. The idea was to show you how it works, not so much to show you how to overhaul one.